Hello, my name is Robert Mitchell and welcome to this podcast for Electropages. In today's episode we are joined by my very good old friend Travis Neumann from Omnetics. And we have a brand new guest who's currently hiding from the camera because he's a bit shy about his face. So could you just give the audience a quick view of your face and tell us who you are?
Hi, my name is Eric Bergquist. I'm a project engineer at Omnetics, so I work with customers to develop custom applications that take our standard products and add some functionality or requirements that are outside the standard. And so we'll do basically anything that the customer needs so long as it's possible.
There we go. And so when you talk about outside the standard, we're not talking about maybe 50 degrees off, we're talking hundreds of degrees, let's say if it was temperature as an example.
Yes, exactly. Our standards might go up to 125 C.
Right.
We've got high temperature capabilities that are well tested up to 200 C. And then we even have customers with applications where they might need to withstand 400 C for a couple of seconds. And so we've done things with very thick fiberglass insulation over the wires that allows us to survive within that time period at very high temperatures.
Wow, 400 degrees, for those watching, is, last time I checked, quite hot. And so what kind of applications would you expect to see these kind of cables when they're operating at such huge temperatures?
I'll just say this, Robin. One of the applications that's recently been inquired to us came from space. And it's in the form of a number of companies are developing electric thrusters, which may use like a xenon gas or similar for the propellant. And one thing that they require is a high current, high voltage in a number of instances, and they want to connectorize these thrusters high temperature. So at the Utah SmallSat show, we had inquiries. It was not uncommon for people to ask at sustained 250 C was a very common number. And then another company that was a xenon gas thruster. They were 330 C continuous is what they're
330 C.
Correct. That's what they were looking for currently. Yes. And reason being is you can't get rid of the heat, so you just need to be able to manage it when you're in space. So
I suppose because you haven't got any gas, so you can't convect it or conduct it away. So all you've got is radiation, and so trying to get rid of that heat, I can see that being a real issue. But seriously, 300 was it 350 or 330?
Either or. At that point, it
wouldn't matter. At that temperature, it wouldn't matter, I suppose.
Yeah,
that's ridiculous.
Was right, and they're going, and these companies are going around and they're asking a number of people if they have a solution, right? So what they currently end up doing is there's no connectors, so they end up hardwiring thrusters with. It could potentially be like a something with a nice fiberglass wrap. There's other applications where they may have like a ceramic type of powder inside of a jacket for some level of heat stability, or you name it. I've even seen, this isn't an Omnetics thing, but I've even seen a stainless steel wire with a stainless steel jacket. Imagine that. So, and that was ultra high temp type applications as well.
How does that work? A stainless steel wire with a stainless steel jacket?
That's a great question. So it's an interesting process, and where my portion came in is I actually made some wire stripping machines for a company in town, and they start with the stainless steel core, and for lack of a better term, they put some sort of a mesh, like call it a stocking, nylon type thing, but some sort of fiberglass like mesh sleeve over the core, and then from there they have a larger diameter stainless steel tube that slides onto that whole assembly. Now you're not making this continuous. This isn't some extrusion line where you've got 1,000 meters or something like that at once. They're making short wires, and then they swage the jacket down onto the core, and that thin little mesh insulator is enough to keep them apart, such that
Oh,
you
wow.
have a stainless steel core wire with a stainless steel jacket. And that's ultra high temp use there as well.
And that jacket, is that a solid piece of steel, or is that like a woven, did you say, sorry, solid?
Absolutely. It's as you can imagine, it is very much, you have a piece of wire that might be, for this instance or this application, we're going metric today, 300 millimeters or so.
Oh, good metric.
Yep. I'll do what I can for you, Robin.
We all know metric is the superior system.
So it'll be 300 millimeters, let's say, because from point A to point B is not a far reach. And then the sleeve similar length, maybe slightly longer, the mesh, and then there's a tube, just a stainless tube, same length, and that slides over the top. So you have these three pieces that are kind of loose initially. You can move them around, and then you put it through a process where it draws that tube down. It'll stretch it out some.
Oh, I see what you mean. Yeah, of course, and it'll clamp it down over the mesh in the core as well.
Yeah, yep. It'll swage that tube down, and then from there, we would on that particular project, we'd use like a diamond saw to cut the insulation and strip the wire, so it can be used for the monitoring device. That one is a monitoring device.
So how on earth do you terminate something like that?
Kind of regularly, honestly. I mean, it's a solid wire, which is not ideal for crimping applications. No. You can make it work with some technologies, but generally stranded wire is going to conform into the crimp a lot better than solid core. Otherwise soldering, probably not a great idea, just given the heat range. You might need to go to something like brazing.
It's a solid piece of metal. There's no way you're going to solder that bloody thing.
It takes a lot of heat.
It's stainless too, which is not ideal for soldering.
Here's one of the other things though too, maybe whether you remember it from materials. So there's like a phase diagram of sorts. I'm murdering the name right now. But the reality is you can have a base metal and you can have a solder of some alloy configuration, and when you reflow that, the solder will leach from like let's say surface A and surface B. So it may reflow the first time at 320 C, and then once it leaches those other atoms of metal in, it changes the temperature such that you've got it hot and it's liquid the first time, but now if you wanted to, I'll call it rework it or remount it or whatever, you can forget that idea that you're going to get it at 320. You're looking at 400 or some higher number because of how the diagram changes for the metals. And again, I know. And
so your everyday 40-watt iron is not going to cut it, basically.
Say that again.
Basically, your average 40-watt soldering iron is not going to cut it.
Yeah, you got that.
No, it's all day feeding all the solder. It'll never work.
Yeah, or an induction heater or something of that nature. Correct.
That's incredible. Absolutely incredible.
Mm-hmm.
But you were saying that's something that Omnetics hasn't done, but you worked on yourself, right?
Yeah. So it's just I'll call it past lives. It was before Omnetics. But in terms of high temp, just kind of curiosity things that exist, I thought it was worth mentioning. That particular application was for they had a large flanged flow meter, and it was to put in the pulverized coal into a power plant. So they have quite a number of these coal monitoring valves, and then that's how they manage the power output and the temperature in the boiler.
Oh, I can imagine, yeah.
I should mention though, he's talking about an example outside of Omnetics, but if a customer came to us with conductor material that's stainless with fiberglass insulation, Omnetics excels at analyzing a customer's specific needs and figuring out whether we can apply our contact technology to their materials. And so we do, countless different experiments every month to just test out different wires and see whether or not we can fit them into our workflow.
So on that topic of sort of like harsh environments, we also talked. So in the past, we've talked about flex cables. We've talked about your special projects team, which kind of is able to look at unique situations and develop custom solutions for that. But are there any new technologies you've been currently exploring that you may be able to offer customers?
I'll say there's exploring right now off the top of my head. I wouldn't say we're doing anything that's really off the wall. I'll say that.
Oh, I don't know about that.
But
or is it a trade secret?
No. There's no trade secret. Fire away.
Well, okay, so I've been working on a potential new product that I won't go into too much detail just because we haven't done any significant testing on it. But what I will say is we're using stainless steel 3D printing to see if we can incorporate flexible members into very, very small metal shells that will allow us to kind of bridge the gap between our strip connectors, which are just plastic, and our bilobe connectors, which have the same connector pitch and contact technology, but they're in nickel-plated aluminum housing. So the aim is basically to have more of the ruggedized characteristics of that nano-D bilobe connector while going more towards the size envelope of the plastic strip connector.
So you're trying to make smaller connectors that are more ruggedized, essentially. And what industries would these be used in?
A whole bunch of things. Honestly, I haven't talked to a whole lot of customers yet because I'm just starting to get to the point where I have real world samples to start talking with people about. But for example, anywhere where there's going to be like a high vibration environment where the customer is worried that without some sort of positive retention feature, the hold of the contacts themselves might slowly jiggle out. There's also a big case for metal shells when it comes to mechanically retaining the connector onto boards, because generally with our plastic connectors, the only mechanical connection to the board are the electrical leads that are soldered down themselves. And with large connectors, that's actually plenty strong, but with smaller connectors and with surface mount connectors, that can be relatively weak. And so you can incorporate solderable pins into the metal shell connector that do the job of mechanically retaining the connector so that you don't put so much stress on the leads during regular use that they peel the pad off.
And is that interesting thing you mentioned there about having solderable pins to act as like a bit of mechanical to give it mechanical strength? Sorry, is there any particular reason why you couldn't do that with a plastic connector?
We have that also, Robin, and that actually stems. There was a oil and gas customer that had asked us about that. One of the issues they had is they would use a surface mount connector and they would use epoxy to stake it because they're drilling and it's high shock and vibe. And one of the things is the oils and such would get on it, and the epoxy would eventually just break down.
Really?
That they're using in their assembly. So we had somebody ask, hey, can you come up with another option for us to be able to stake this and get rid of the epoxy step? So on our small strip latching connectors, and I have some sitting over here, but not that one specifically. We consume one of the spaces for the latch. That is the guide. And this is probably going to be hard to see, but because everything's small.
It's an incredible amount of blur.
Basically, there's a plastic insulator, the black plastic insulator, and then there's the shiny metal latch.
And there would be a pin that we put in that aligns with that latch, if you can see it. And what that allows them to do, depending on their process, they can pin and paste it using their standard screening process during surface mount assembly, or you could screen print your normal surface mount and then follow up that particular staking pin, we'll call it, with a selective soldering process, and then skip having to have a person or a machine later on down the line hand stake it with epoxy.
Right.
So we do have.
And so like, you've automated the process of manufacturing, but you've also been able to. I take it the new connector was also able to resist the oils that were found in the drilling well as well.
It's the same materials we've used generally, like an LCP or PPS.
Yeah.
That doesn't have the issue
it's
that.
Sorry, it's the epoxy that glues the connector to the board. Sorry, I'm with you. Yeah,
correct.
I'm with you, yeah.
So we provide the customer with the connectors, and then couldn't tell you what epoxy they chose for their application.
Probably some standard off-the-shelf two-part epoxy they weren't supposed to use.
Honestly, that's very possible.
Honestly, it could be.
We have no idea what our customers are doing.
I'm not sure what your hardware store is in America. What is your hardware store? Is it what would be your big brand of hardware store? Ace Hardware, is it, or something?
Yeah.
All right. So you can imagine some engineer who's got a budget of a couple of £1 million. Goes, oh, it's $2 part outright. That'll work. Just use that on the board, basically. So funny.
You say that like it's even remotely.
It probably happens.
I think the main thing is an engineer that is. An engineer worth their salt will always test the simplest solution first.
Yeah,
and there may be some reason to just outright say that epoxy not rated to the right temperature, whatever.
Right.
But if you don't have a reasonable reason to not use the cheapest possible thing, why not try it?
Yep.
And so when once you develop that solution. What else could have that been used in as well? So, except for the oil industry, what other sort of solutions could that have been used for?
Well, that's another thing that chimes right into everything else ruggedized. So, there's a number of UAV type applications. They one in particular, Lockheed has a small drone that they backpack, and they build it in stages, and when they get to the point where they're connecting the 4 motors into the board, they use these style connectors. So if it's in some other type of small, because of those are micro connectors, small application, they can run 3 amps and they need latching and all of that, it'll definitely check the box. I've got a number of colleagues that are now out in industry that talk about using hardware, and if you don't use that correctly when you install it, you're going to have issues down the road, that sort of thing. Or there might be some of these guys will even use screws and they end up using epoxy as well, just as a secondary mounting option or backup or that sort of thing.
And so you're just adding reliability by having multiple mechanical methods of holding that connector down to the board. But the connector itself, even without that additional epoxy, you've still got those extra pins for soldering. It keeps it down. It's good for ruggedized environments.
Correct.
And I also take it that means that not only could you make those connectors ruggedized, but then handle those extreme environments.
Right. And the thing is too, like traditionally, I think you had mentioned it earlier, Eric, or maybe that was when we were speaking to Jack. Traditionally, they would go for through holes because that gives you a really great amount of support through the board. And this is kind of a mix of both, right? So you have a through hole, you still have that through hole support, and you have your surface mount as well for ease of assembly.
Right.
So it helps with, if a person's doing work by hand, it helps to line the connector up and all sorts of other things.
Oh, I didn't think about that. That's quite useful, isn't it? Because you can just, if you get your tolerances right, you can pop it straight in and the pins will match exactly where they need to be.
Right. You could sit at the desk you're at right now, and if you have a board soldered up and place those connectors, and have no problems getting them to the pads to line up and everything else.
And is that still compatible with your typical pick and place processors?
Generally, yes.
Generally, yeah.
The main thing you need to have is the closer the pin is to the diameter of the hole, the harder it's going to be. But,
of course, you have tolerances, won't
you?
You
Can, exactly. Right. However, because this is kind of a purpose-built pin used for alignment, we can add chamfers into it so that it corrects.
I was literally about to say, could you not have a pin that's kind of conical in shape so that it'll always find the hole that'll go straight through correctly?
Absolutely.
Oh, how brilliant.
Yep, and we don't generally do that with the leads of the connector just because that would be a significantly more expensive process than trimming a cylinder to length. But when we have these purpose-built pins that are solely for alignment, we can do whatever we need to make them more robust.
And on a customer side too, if you know your process. So I had mentioned pin and paste or selective solder. If I'm going to do pin and paste, that means generally I'm going to want the hole to be closer in terms of the size of the diameter of the pin, just because of the filling that guy up with solder. But if I'm doing selective solder, I could put a larger mounting hole on that guy because I'm going to flood that whole cavity and it's going to solder regardless. So you've got some options too, and when you design it on your end as a customer for how you wanna do that mounting pin. So,
Now, one question I would like to ask you. Now, this is the part of the podcast where we may have to cut it out, but I'm kind of interested in the conversation you had with Jack before this podcast, and you were mentioning, I think you were mentioning about munitions and 30,000 G. It kind of just went over the top of my head briefly, but from what I understand, you were talking about essentially guided munitions at high velocity.
Yes.
Is that something that Omnetics could basically do?
Well, we'll sell you the connectors. And
you sell the connectors and that's it.
I'm going to say it like that, and then you can cut out whatever you want to cut out. We have customers that are absolutely working on that project, that type of project, with that type of work. We're high reliability. A lot of our business is in mil aero. We don't shy away from that. So one of the things that we've had customers come back to us with is they've put some of these connectors into their assemblies. They've shot them out, and the connectors peel right off the board. Right. So you could almost imagine like a kid's cartoon or something where one piece stays put and the rest is gone. And then what that lends into then is like, okay, let's work together and find a mechanical route for this thing to stay put. That might mean that there's epoxy plus hardware. That might mean that we make specialty mounting pins. That might mean that they change from a larger micro-size connector down to a nano, right? Because F equals MA. So
actually, I think you'll find the correct formula is actually that A equals F over M, because A is the subject of the formula. Thank you very much. I always get very funny about that. Same with V equals IR. I always say it's always I equals V over R, but that's just me being particular. But that's a very interesting concept. I think I've almost broken Travis there.
That's what I need to do.
Brilliant.
Okay, please continue.
But, sorry, we've got our time.
But on that note, though, so what size munitions are we talking? Are we talking sort of large artillery shells? Are we talking close down to like 30mm type of smaller?
155 is a real popular howitzer. I believe the howitzer is a 155.
Yeah, I think that. Yeah, oh, yeah, it is 155, isn't it? Not 150. Yeah, it's 155. It's a NATO standard, isn't it?
I believe so. Yeah.
And so the idea is that when these things are shot out of cannons, even though you've got your what do you call it? What do you call it? The word when you've got your directions right and you've got your target sighted, you've got your
trajectory.
Yeah. Thank you, your trajectory. You've got everything right, but even then, during transit, you'll have wind coming in, you'll have G-forces, you've got the Coriolis effect, and all those things are going to change where that shell lands. And so the idea of putting smart devices into munitions that it can then adjust its flight path to hit the target precisely. And
Right.
so the connectors you have to design have to be able to withstand immense G loads and temperature changes.
And that's the thing too. So like just from the first description, right? When it's being shot out, that's just one direction of G-force.
Right.
So as you can imagine too, this thing
Spinning
is
as
spinning
well,
as
yeah.
it's going through the air. So there's some level of centrifugal type of force that engineers need to account for as well.
And so you've got a poor old cable having to withstand this huge sudden impulse being fired at the cannon, then being spun around really, really quickly. And so in those applications, what kind of connectors would you think would survive or have the biggest chance of surviving?
Well, by far the easiest way to make a connector survive high acceleration is to reduce its mass, and that is really where we excel because, like, the connector that I showed you earlier, it's a micro-sized connector. That is the bigger size of connector for us, and you could barely see it. So that's what's the conversion there? 1.2 mil pitch.
Yep. 127.
127. Yep. We have half that pitch in our nano-sized connectors, and the combination of the smaller pitch, the thinner insulator that comes with that, and then also the shorter mating length means that through whatever you want to call it, the square cube thing, where when you reduce the dimension of something by 2 times, its surface area goes down 4 times and its mass goes down 8 times. That is what you get with these connectors, and it's actually really impressive because the weight of our nano strip connectors, so the ones without a metal shell to increase its mass significantly, the mass of those connectors is actually so small that even just the engagement force of the contacts themselves is sufficient to reliably keep them connected under G loading of 100 Gs or more, which you just wouldn't see in a heavier connector.
Right.
And that, along with things like you can bond board mount connectors to flex strips, as I believe you've talked about before, which means that you've got much less mass in the electrical path. Means you can really reduce the actual kind of overhead weight of your electrical system and thereby increase its reliability.
Now,
high acceleration.
Now that's one thing that never really occurred to me. If someone said to me, you've got to have a cable that's going to survive being shot out of a cannon, I would think of a huge chunky cable with big bolts and all that kind of stuff. But what you're actually saying is the smaller you go, the higher the chance it's actually going to survive because it's got a lower mass.
Exactly. And, the only other real things to account for is just from a systems design side, you just want to make sure that cable is well secured to parts of the frame, and it's got sufficient slack such that if there's a small amount of motion of like components relative to themselves in that enclosure, not going to put undue strain on the connection, whether it's to the board or the mating connection. As long as you do that, it is pretty simple to design very high acceleration and shock systems with these types.
And I also take it that it's in a situation with a cannon, it's actually the first few, I'm not sure, maybe less than a few milliseconds is where you actually get your initial G-force. But once it's in motion, it's the circular rotation of the shell that's actually inducing those continuous G-forces. But you're not experiencing any additional G-force because the acceleration's already accelerated to its maximum speed. And so I take it that so like with temperature, for example, a cable can be made to withstand, let's say, 300 degrees for a few seconds. Is that the same for G-force? Is it you can make things survive for a short period of time, or does it not matter?
There is some argument for, from a system reliability perspective, the shorter amount of time that the electrical contacts are experiencing that shock, it basically comes down to electrical interruption. You have to limit the electrical interruption to a certain amount of nanoseconds over the length of the test. And from the data integrity side of things, it's basically how much overhead do you need to leave in your system for checking that the data received is not damaged in some way. And if you only need to overcome that like 10,000 G acceleration for several milliseconds, the design of the system as a whole can be a lot less complicated, just because you can basically plan for the system to have a small blackout during that time. So that's pretty, it's a less complicated thing to design for. However, you can't deny the fact that that centripetal acceleration that it experiences can also be several thousand Gs.
Right.
So that is a more continuous problem that we can also resolve.
You can handle the.
And I imagine that momentary blackout's quite important, because if the shell's fired and it thinks it's already landed its target, because of electrical disruption, it's starting to blow up in the actual cannon itself, as opposed to when it hits its target downstream. And well, depending on the fuse it uses, I suppose.
I mean, you could use that. You could use that initial strike, I'll call it, as a like a delay on timer, right? Depending on how you have something made. Like, think about it like, oh, I have what would be another example? I think of like a smelling salt or some of those glow sticks, right? So you'd have it oriented in such a way that once you hit that acceleration, it pops, and then that tells you, okay, now I'm starting to pay attention to the rest of the world.
Now,
and that might be some trigger event of I need 20,000 Gs or whatever, and then I break that to turn it on. Whatever.
Now, on the topic of extremely fast munitions, how would Omnetics actually go about testing that? Because I don't think you guys would turn up in a van asking the US military, oh, can I just borrow a howitzer for the afternoon? Would you mind? And just set it up in the car park over there.
Yeah,
I can imagine you've got your competitors' buildings across the road. Just this huge cannon pointed towards. All right, test it. 3, 2, 1, go.
Maybe across the city.
Across the city.
So we do partner with a testing company that has shock and vibration apparatuses that can go up to kind of more reasonable shock and vibration that you might expect in most applications, like 100G, maybe up to 300G.
Right.
However, generally the testing procedure for extreme high G applications is complicated enough that it really doesn't make sense for the supplier to be responsible for it. And that's where we partner with our customers.
Yeah.
And they, if they're willing to let go of that data, they will actually send us test reports. And we have received test reports before where our connectors have been validated through real life testing up to 10,000 G.
Yeah.
And so it really is a partnership between us and our customers to validate that sort of application.
And that goes into what we were talking about, I think, before we hit record, and that was call it buy it and try it. So we make some up, we make 5, 10, whatever, so that way if they want to do a drop test, let's say, to simulate it impacting, or some other type of test that they want to do to figure out if the entire system is working, that's where we come in. Yeah, the real exotic stuff, the customer's going to take care of that generally.
And which kind of makes sense, because it's a bit unreasonable to expect you guys to start firing shells into the car park to try and figure out if they're going to survive. And I suppose there's no realistic test jig I could imagine that would be able to simulate 10 to 30,000 G anyway, so I don't think it would exist.
Some sort of explosion or something.
Somebody at NASA could probably talk to you a lot more about IT test jigs, but it's certainly not it's not a commodity item.
No, of course. Now, on the topic of extremely harsh environments, has Omnetics got a cable able to survive lava yet?
So
well, let's see. That's a loaded question, because I could just say yes because there's nobody around to test it. So how do you want to look at that?
Well, I would say that a big component of that question is, how long do you need it to survive in lava?
Yeah, that's right.
It's very viscous, so I don't know if you're actually going to be able to take the cable and really shove it into the lava. So I believe it's just going to be surface contact.
Right.
And for surface contact, radiative heating, we've got, reflective shielding that can probably help with that. And then, if you needed to survive for 10 seconds, maybe we can just take a cable harness and put 5 layers of fiberglass insulation over it, and it would probably survive for 10 seconds.
And is that something that has a customer ever actually asked for something to survive in an environment like that?
Yeah, well, not necessarily. As far as I'm aware, lava tends to be in the several thousand feet range, which is a bit in excess of most customers' needs. Even in the center of a rocket engine, you will not find temperatures that high. But we do have customers that have high temperature requirements where it might be 400 C, and if that were continuous, fundamental parts of the connector would break. Our contacts, beryllium copper, that is not a suitable material for that temperature long term. But if they need it to last for 30 seconds, which I think this customer needed it to, with sufficient insulation, that will not infiltrate fast enough to start damaging delicate parts of the system before that heat is taken away.
Right.
So it really is something where if you've got an application like that, we can help.
And so on that, I can see him laughing already about that.
I'm
go
good.
on. Go on. So on that topic of so in the talk about the heat, the way that your cable would survive is that it's thick enough and able to resist the heat transfer, such that you would be able to handle it for maybe 10 seconds, and then you have like a cool down period where the heat's removed, and then as the heat's kind of like traveling through the material, it's getting lower and lower as it gets to the core, and then once you get down to a certain point, you can go back into that heat again. So I'd imagine it's kind of like I'm not sure what you call it, but yeah, you basically got like an on and off time. So so would you normally say that the on time is a lot shorter than the off time?
It's entirely what.
But it depends on the system, right?
It completely depends on the system.
Yeah.
So there's in terms of insulation performance, any insulation material will be able to dissipate a certain amount of heat per unit distance. So theoretically, if you've got a material that isn't going to break down at the operating temperature, which is its own challenge sometimes, so long as you can get thick enough insulation on it, you should be able to maintain any sufficiently close to room temperature level within that insulation. It just becomes a question of when does that thickness of insulation become impractical.
Yeah. You can't have a cable this thick for something that's like the size of a head. It would be
exactly,
ridiculous.
Or it's so thick the wire doesn't bend anymore. At which point it kind of doesn't. It's not a wire anymore. So there is kind of a direct relationship between the thickness of insulation where you could operate continuously and the thickness of insulation that you can use where it's still useful for the application, and that difference is basically going to directly relate to the ratio of on time to off time, your duty cycle.
I see.
Cooling.
Right. And so just out of curiosity, since it's been a little while since we last spoke to each other, what is the weirdest project you've seen till this day?
Let's see, the weirdest. Well, the one I think of is there's that one that's maybe it's not weirdest, but it's definitely a challenge. It's 4,500 volts.
Exactly what I was thinking.
4,500 volts, 70,000 feet of altitude.
40,000. 40,000. It was just 40. which, and actually this is interesting
that's right.
context.
He was because he was derating it. That's right.
So
that's right. That's right.
Another rugged environment that we need to deal with is high voltage at altitude.
Yes.
And if you're not familiar with dielectric withstanding voltage and voltage breakdown, it's basically past a certain voltage, the insulation of the wires and with the connector itself will not be sufficient, and current will actually arc through the connector. That is what basically defines the level of insulation you need. And that level of insulation, the requirements actually become higher as you go up in altitude, up to about 70,000 feet, because with less and less air molecules kind of insulating the connection, it becomes easier and easier for that current to flow places you don't want.
So so imagine, so just make sure I've got this right, you've got two cables with a dielectric around them, and you're saying that if they're in a vacuum, it's easier for current to jump that gap?
No. Okay, so that's why I bring up 70,000 feet of elevation. Right. So there is kind of a curve of withstanding breakdown. So at sea level, there's so many air molecules that they kind of muffle the breakdown path.
Like 50 volts per mil.
As it gets down to, as you go up to about 70,000 feet of elevation, that effect is reduced to the point where you're at your greatest risk for breakdown.
Right.
But breakdown through air has to happen in a medium. It has to have atoms that it can ionize to produce a path. And so within a vacuum, breakdown is actually much higher. Is it more of a
parabolic? Can't say the word, like a parabola. No, you know what I mean. Does it do this?
Yeah, you're good. You're good.
I don't know the exact mathematical, theoretical definition.
And I imagine the reason why it might be like that is that you've got just enough air to ionize where its path is undisrupted, so it's very easy for it to go across. But if you have too much air, it's kind of packed, and then it's hard for the charge to get across. Right. That I never thought about. So you're going up in elevation, and it actually becomes worse. Then you get beyond that point, then it gets better. And then and a weird question then is, what's the dielectric breakdown of a vacuum? Is it just nothing? Like it won't happen, or is it?
So, I don't know the theory. All I know is that there's no such thing as a pure vacuum. So to some extent, there's always going to be something for electricity to grab onto. But at some point, the energy going through a vacuum will be almost exclusively radiation. So electromagnetic radiation, light, radio, all of that can travel as a wave through a vacuum. And things radiate out as heat, as infrared. It just becomes a question of, at what point do you just not have enough voltage for it to even matter?
I also imagine if you're in vacuum space, you've got the sun nearby, you've got a ton of gamma radiation and X-rays, and so I imagine that's going to ionize the metal in the first place. It's going to knock things off like electrons, and so it's already going to start jumping across the two.
Yeah, that's very much so. There's people that have one of the big themes that's coming back in my mind. I'll say coming back is hardened electronics and such, because stray particles can very much change a bit from call it a 0 to a 1 when you're doing microprocessing and such in space, and cause all sorts of chaos. So absolutely.
And so going back to this 4,500 volts at 70,000 feet, was it? Yeah. So what's going on here then?
Yeah, so this is actually one of my favorite applications that I've seen go through the project engineering team. So the breakdown voltage rating for a standard micro D connector, which we're basing this off the micro D military spec, is 600 volts, and at 70,000 feet it's 200 volts. So that's a far cry from the 4,500 volts that the customer was looking for. And so this is breakdown voltage, which so I believe their actual operational voltage was 1200 volts.
Right.
So you generally rate down voltage by 3 to 1 to get to your operational voltage. And we went through, my colleague Hunter went through iteration after iteration trying to it's like trying to fix all the leaks in a boat, because as you get the most likely candidate for where that voltage is, where that current is leaking, it just shows up in weirder and weirder places, to the point where I think one of the last things he fixed was actually it was traveling up the wire and arcing across the back of the very back of the connector and back down. And so that was kind of one of the final little leaks before we actually got to the limit of our voltage tester, which is 5,000 volts. And the key development that he did to make that system work was actually, we call it a volcano.
Here we go again.
It's effectively, you need to look at the surface breakdown path. So basically the amount of distance that arc has to travel between 2 points of different voltage. And the way we did that was actually, for one pin in the entire connector, we flipped its gender. So it went from a pin to a socket, or vice versa. And that meant that the mating surfaces had to either sink deep down into the connector to expose that socket, or push out to protect the pin. And so we, you dramatically increase the distance that the path has to travel between those 2 voltages. And then finally, he needed to test kind of a sealing capability.
We added seals.
And it's basically an O-ring that sits down into the bottom of that reverse volcano, and seals it up once the 2 connectors are mated, so that there is as little gap as possible for that voltage to go through. So for reference, sizing wise, unfortunately we can't fit that technology into a standard 2-row connector. It has to be a 4-row connector to fully enclose that volcano. But it's very compact.
Because otherwise the housing becomes a path of production. Because that's the other thing. We built a number of these things, and I got to watch them. I got to watch the test where Hunter and I were working on it, and it was. I mean, we added extra insulation to the path, that main wire, all sorts of things. We 3D printed molds for those. You name it.
And during the test of that cable, it didn't make any of the magic smoke by any chance, did it?
Oh, it absolutely did. That was
every failure.
That was the great thing about it. So I think it was on the first set. I was in the lab and I was helping Hunter. We were messing around with that, and he ran the tester up to 4,500, and we just went for it. And we heard a noise, and he's like, did you see anything? It's like, well, let's just shock it again, because once it's shocked once, the path is there. So it's like, okay, over on the other side, he hits it again, boom, we can see where it's at. Then it's like, okay, it's fixing the leaks in the boat, right? So now it's like, we see where it's sparked from the main line at voltage to one of the other contacts that are close by, and then it's like, okay, let's add some insulation, let's do this, let's do that. So
fantastic.
It's a neat project.
So before we wrap this podcast up, I'd just like to ask you, is there anything you'd like to say to the audience about Omnetics and what you guys are doing at the moment?
As always, we're doing a fair amount of new product development work, as Eric very much mentioned, and that's what we do in special projects. We've had a number of applications that are requests for applications regarding space. That's been very recent, a lot of recent stuff.
Yes, actually, I should mention.
So
the standard cable harness workmanship standard is WHMA IPC 620.
Correct.
And that has multiple classes, and it also has an addendum called the space addendum. And a large number of our customers are going towards that addendum because it makes their process easier if they just tell all of their vendors, you need to make everything to IPC 620 space.
Right.
And because we had so much interest in that, my colleague AJ headed up the process of getting us certified to the space addendum. And now we actually have, I think, over 30 operators who have been trained and qualified to produce space addendum level hardware, which means that basically anyone who needs space cables, space connectors can count on us to be making them to the highest level of workmanship standard.
So instead of sending new Omnetics employees into the pits of volcanoes, you'll now be shooting them into space on Elon Musk's next rocket, which will probably blow up. But as we said before, your cables are, our staff is expendable, but your cables are not.
Well, that's your meme, but
pretty much.
Sure, that's your meme.
Pretty much. And we've definitely got to post that one out there because I think it's absolutely brilliant.
You know, one of the interesting points too, Robin, was when I was at that space show, there's another wave of companies coming up because everybody and their brother believes that they're going to make some device and rent time on the Falcon rockets. It's all the times leased. So there's kind of what I'll call another wave of new space type companies that are coming, that are making rockets, launch systems, and everything, just so people can get their devices up.
It's an exciting industry for sure, and it's going through a lot of changes at the moment. So and like you say, I suppose Omnetics is ready to take on that challenge for customers who want to go to space.
Absolutely.
Fantastic.
Absolutely.
Well, thank you ever so much for taking the time to see us today here on Electropages, and I'll see you guys next time.